Here's what nobody tells you about the universe. It's mostly empty. Not the poetic kind of empty where you stare at stars and feel small. The kind of empty where if you picked a random spot in existence, there'd be nothing there. No light, no atoms, nothing but void stretching for millions of light years in every direction. And that's just one of the problems with trying to understand this place. Right now, you're traveling through space at over 1 million miles per hour. You don't feel it because everything around you is moving with you. The Earth spins. The Earth orbits the Sun. The Sun orbits the galaxy. The galaxy moves through space. All of it happening simultaneously, and you're just sitting there reading this, completely unaware that you're caught in this cosmic dance. But here's what makes it stranger. When you look up at the night sky, you're not seeing the universe as it is now. You're looking back in time. The light from the nearest star took 4 years to reach you. The light from distant galaxies has been traveling for billions of years. By the time it hits your eyes, those galaxies might not even exist anymore. So let's do something most people never attempt. Let's try to explain the entire universe in 60 minutes. Not the simplified version you learned in school. The real one, with all its contradictions and mysteries intact. We'll start small, with our own cosmic neighborhood. Chapter 1. The solar system's hidden depths. You probably think you know the solar system. 8 planets, some moons, maybe an asteroid belt. Simple enough to draw on a poster board. But zoom out just slightly, and that comfortable picture falls apart. Beyond Neptune, where your mental map of the solar system probably ends, there's an entire population of worlds we barely understand. The Kuiper Belt stretches from Neptune's orbit to about 50 times Earth's distance from the Sun, packed with thousands of icy bodies. Some are barely bigger than mountains, others rival Pluto in size, and Pluto itself. We only got our first clear look at it in 2015. Before that, the best images we had were blurry pixels. When New Horizons finally arrived after 9 years of travel, it revealed a world of frozen nitrogen plains and mountains made of water ice harder than steel. But even the Kuiper Belt isn't the edge. Another 20 times further out, you enter the Oort cloud, a spherical shell of comets surrounding the entire solar system, extending nearly halfway to the nearest star. We've never directly observed it. We know it exists because every few thousand years, something disturbs one of those comets, sending it plunging toward the inner solar system, where it becomes visible in Earth's sky. The Oort cloud contains roughly 5 Earth masses worth of material, scattered across a volume so vast, it defies comprehension. If you wanted to visit every object larger than a kilometer across, traveling at the speed of light, it would take you years just to complete the journey. And this is just our backyard. The Sun's gravity dominates space for about 2 light years in every direction. That's the true extent of the solar system. Not the neat diagram with planets lined up in a row, but a bubble of gravitational influence extending into the darkness, filled with debris and ice and mystery. Now imagine making the jump to the next star. Chapter 2. The void between Proxima Centauri sits 4.2 light-years away. That's the closest star to our Sun. If you could somehow travel at 1% the speed of light, which would be faster than anything humans have ever built, the journey would take 420 years. But you wouldn't be traveling through empty space. Not really. The space between stars is filled with something. Hydrogen atoms, a few per cubic centimeter, dust grains, cosmic rays, the occasional molecule. It's called the interstellar medium, and while it's far emptier than the best vacuum we can create on Earth, over the distances between stars, it adds up. Voyager 1, the spacecraft that's traveled further from Earth than anything else humans have made, crossed into interstellar space in 2012. It took 35 years to reach that boundary, and now, moving at about 38,000 miles per hour, it's crawling through the void at a pace that would take it 70,000 years to reach another star, if it were aimed at one, which it isn't. The spacecraft carries a golden record with sounds and images from Earth. Music, greetings in different languages, pictures of people and places. A message in a bottle thrown into an ocean so vast that the bottle itself is smaller than an atom compared to the distances involved. And yet, the space between stars isn't the loneliest place in the universe. Stars cluster together into neighborhoods. Our sun belongs to the Orion Spur, a minor arm of the Milky Way galaxy. Within about 30 light years, there are roughly 400 stars. Some are dim red dwarfs, barely visible even if you could get close to them. Others are binary systems, two stars locked in orbital dances around each other, and a few are dying. Betelgeuse, one of the brightest stars in our night sky, sits about 550 light years away. It's a red supergiant, already in the late stages of its life. At some point, possibly tomorrow, or possibly in the next 100,000 years, it will explode in a supernova bright enough to be visible during the day on Earth. When it does, we'll be watching the death of a star that actually exploded 550 years before we see it happen. The light carrying that information will have been traveling through space since before the invention of the telescope, finally arriving to show us an event that's already ancient history. This is what makes astronomy different from every other science. You can't run experiments. You can only watch and wait and try to make sense of patterns that unfold across timescales no human will ever experience. But it gets stranger when you zoom out further. Chapter 3: The Galactic Scale. The Milky Way contains somewhere between 100 and 400 billion stars. Nobody knows the exact number because we can't see most of them. Dust clouds block our view. Dim stars hide in the glare of brighter ones, and we're stuck inside the galaxy itself, trying to map it from within. The best estimates suggest the Milky Way is about 100,000 light-years across, a spiral galaxy with 4 major arms and several smaller ones. Our solar system sits about 26,000 light-years from the center, embedded in one of those minor arms. At the core of the galaxy, hidden behind clouds of dust and gas, sits Sagittarius A star, a supermassive black hole containing about 4 million times the mass of the Sun, compressed into a region smaller than the orbit of Mercury. We can't see the black hole directly, but we can watch stars orbit around it, moving at speeds up to 3% the speed of light. Their motion reveals the invisible monster at the galaxy's heart. This black hole isn't unique. Every large galaxy appears to have one. Some are far more massive than ours. TON 618, one of the most massive black holes ever discovered, weighs in at 66 billion times the mass of the Sun. Its event horizon, the point of no return, would stretch beyond the orbit of Pluto. But even these cosmic giants are tiny compared to the galaxies that contain them. The Milky Way has satellite galaxies, small collections of stars orbiting around it like moons around a planet. The largest, the Large Magellanic Cloud, contains about 30 billion stars. It's being slowly torn apart by the Milky Way's gravity, its stars and gas stripped away and absorbed into the larger galaxy. This process of galactic cannibalism has been happening since the Milky Way formed. We can see the remnants of ancient collisions in the distribution of stars, streams of material stretching across the sky like cosmic rivers. And in about 4 billion years, we'll collide with Andromeda. Our nearest large galactic neighbor sits about 2.5 million light-years away and is rushing toward us at about 70 miles per second. When the two galaxies meet, they'll merge into a single elliptical galaxy over the course of billions of years. Individual stars almost never collide during these mergers. The distances between stars are too vast. But the gravitational chaos will fling solar systems in random directions, reshape both galaxies completely, and trigger massive bursts of new star formation as gas clouds slam together. Humans won't be around to see it. But whatever exists on Earth in 4 billion years, if anything does, will witness the most spectacular light show imaginable. Now here's where things really start to break down, because between our galaxy and Andromeda, there's mostly nothing. And when you zoom out to see the full picture of the universe, you realize that galaxies themselves cluster together in ways that reveal something deeply wrong with our understanding of how gravity works. Or perhaps, something invisible is holding everything together. Galaxies don't move alone. Right now, the Milky Way is falling, accelerating towards something massive, something pulling us across millions of light years of space at hundreds of kilometers per second. And we're not the only ones. Hundreds of galaxies in our neighborhood are being dragged along with us, all streaming in the same direction, like leaves caught in an invisible current. But what's pulling us? What force could possibly yank entire galaxies across the cosmos? The answer lies in something we can barely see. Something that makes up most of the universe, but refuses to interact with light. Dark matter. The invisible scaffolding holding the cosmic web together. And this is where things get strange. Because when you look at how galaxies cluster, how they orbit each other, how fast they spin, the math doesn't work. Not even close. There isn't enough visible matter. Stars, gas, planets. Everything we can see only accounts for about 15% of the matter needed to explain what we observe. The rest is hidden. Fritz Zwicky figured this out in the 1930s. He was studying the Coma Cluster, a massive collection of over 1,000 galaxies bound together by gravity. When he measured how fast these galaxies were moving, he realized they were going way too fast. At those speeds, they should have torn themselves apart, scattering into the void billions of years ago. But they didn't. Something was holding them together. Zwicky called it dark matter, an invisible form of mass that doesn't emit, absorb, or reflect light. It just sits there, exerting gravitational pull. Most astronomers ignored him. For decades, dark matter remained a fringe idea, dismissed as an error in calculations or a misunderstanding of gravity itself. Then came Vera Rubin. In the 1970s, Rubin studied how stars orbit within galaxies. She expected stars at the outer edges to move slower than those near the center, the same way outer planets in our solar system orbit more slowly than inner ones. That's how gravity works, when most of the mass is concentrated in the middle. But that's not what she found. Stars at the edges of galaxies were moving just as fast as those near the center. Some were moving faster. The only way to explain this was to accept that galaxies are embedded in massive halos of invisible matter, dark matter that extends far beyond the visible edges of the galaxy, creating a gravitational well that keeps everything spinning at the same speed. The evidence became overwhelming. Galaxy after galaxy showed the same pattern, and it wasn't just rotation curves. Gravitational lensing, the way massive objects bend light, revealed dark matter's presence through distortions in background galaxies. Computer simulations showed that without dark matter, galaxies simply wouldn't form. The universe would look completely different. Now here's the problem. We still don't know what dark matter is. It's not regular matter that just happens to be dark. It's not black holes or rogue planets or clouds of cold gas. Those would show up in other ways. Dark matter interacts with almost nothing except through gravity. Billions of dark matter particles are passing through your body right now, slipping through the spaces between your atoms without touching anything. Scientists have proposed dozens of candidates. WIMPs, weakly interacting massive particles, axions, sterile neutrinos, primordial black holes left over from the early universe. But despite decades of increasingly sensitive detectors buried deep underground, shielded from cosmic rays and background radiation, we haven't caught a single definitive signal. Dark matter remains invisible, untouchable, known only through its gravitational fingerprints. And those fingerprints are everywhere. The cosmic web, that vast network of galaxy clusters, connected by filaments with enormous voids in between, only makes sense if dark matter acts as the foundation. In the early universe, tiny fluctuations in density created regions where dark matter began to clump together. Its gravity pulled in regular matter, gas and dust, which eventually formed stars and galaxies. Without dark matter, those initial fluctuations wouldn't have been strong enough. structure formation would have taken far longer than the age of the universe allows. Dark matter built the cosmic web. We're just decoration. The distribution of dark matter determines where galaxies form, how they cluster, even the shapes they take. Spiral galaxies like ours sit in roughly spherical halos of dark matter. Elliptical galaxies, the red and dead giants formed from mergers, have different distributions. And dwarf galaxies, the tiny satellites orbiting larger ones, are almost entirely dominated by dark matter. Some contain hundreds of times more dark matter than visible matter. But the strangest thing about dark matter isn't what it does, it's what it doesn't do. Dark matter doesn't clump as tightly as regular matter. It can't radiate energy, which means it can't cool down and collapse into dense structures. Regular matter forms stars and planets because atoms collide, lose energy through radiation, and settle into stable configurations. Dark matter just drifts. It forms vast, diffuse halos that extend far beyond the visible edges of galaxies, creating gentle gravitational wells rather than concentrated points of mass. This makes dark matter fundamentally different from anything we experience in daily life. It's matter that can't form objects, mass without substance, gravity without form, and it's not distributed evenly. Some regions of space have more dark matter than others. The voids between galaxy clusters are relatively empty, while the nodes where filaments meet are packed with it. This uneven distribution creates the cosmic web structure, the walls and voids that give the universe its texture on the largest scales. The Milky Way sits near the edge of a void. The local void, discovered in the 1980s, stretches for about 150 million light-years, almost completely empty. No galaxies, no stars, no gas. Just traces of dark matter holding the boundaries in place, preventing the void from collapsing as surrounding regions pull matter away. Standing in the center of such a void, you'd see almost nothing. A handful of distant galaxies scattered across the horizon. No bright clusters, no nearby stars, just darkness stretching in every direction. The cosmic microwave background, that faint glow from the Big Bang, would be your only companion. A cold reminder that the universe is mostly empty space. But at the edges of voids, where matter accumulates, dark matter creates superhighways. Streams of gas and galaxies flow along these filaments, pulled by the gravity of dark matter concentrated there. Our local group, the cluster containing the Milky Way and Andromeda, sits at one such intersection. We're surrounded by the local sheet, a wall of galaxies stretching across one side of the local void. And we're falling toward the Virgo cluster. Virgo sits about 50 million light-years away, a massive collection of thousands of galaxies dominated by giant ellipticals. Its gravitational pull extends far beyond its visible boundaries, drawing in everything within 100 million light-years, including us. The Milky Way is accelerating toward Virgo at several hundred kilometers per second, caught in the gravitational tide created by concentrated dark matter. But Virgo isn't the end. It's part of something larger, the Laniakea supercluster, a structure so vast it contains over 100,000 galaxies spanning 500 million light-years. The name comes from Hawaiian, meaning immeasurable heaven, and Laniakea is just one supercluster among many. Perseus Pisces, Coma, Hydra Centaurus, Shapley, each one a massive concentration of matter and dark matter, separated by voids hundreds of millions of light-years across. Together, they form the cosmic web, the largest pattern in nature. Walls and filaments bridging vast distances, with voids occupying most of the volume. And dark matter holds it all together, the invisible foundation upon which everything rests. Without dark matter, none of this would exist. Galaxies wouldn't form, stars wouldn't ignite, planets wouldn't coalesce, life wouldn't emerge. The universe would be a thin soup of hydrogen and helium, gradually spreading apart as space expands, with no structure, no complexity, no observers wondering why. Dark matter makes the universe interesting. It creates the conditions for matter to collapse into galaxies, for stars to form and die, for heavy elements to scatter through space and eventually assemble into planets and people. Everything we see, everything we are, exists because dark matter provided the gravitational scaffolding, and yet we can't touch it, can't see it, can't interact with it except through gravity. It surrounds us, permeates us, passes through us constantly. More fundamental to the universe's structure than ordinary matter, more abundant, more important, but forever out of reach. A reminder that we're still figuring out what the universe is made of, that the cosmos holds secrets we can barely glimpse, forces and particles operating just beyond our ability to detect them directly. Dark matter is the universe's greatest magic trick, hiding in plain sight while shaping everything we see. Part 3. But here's what most people miss about energy. It's not just about how much exists. It's about concentration, about density, about accessibility. Stars create energy through fusion, converting hydrogen into helium, releasing photons that take hundreds of thousands of years just to escape the star's core. Black holes concentrate matter into singularities, warping space-time itself. Supernovae forge heavy elements in seconds that took stars millions of years to prepare. And then there are cosmic strings. If they exist, they represent something fundamentally different. Not objects made of particles, not even empty space. They're defects, scars, wounds in the fabric of reality itself that never healed after the universe's birth. Picture space-time as a sheet, smooth, continuous, well-behaved. Now imagine that sheet being torn, then sewn back together imperfectly. The seam doesn't match. There's a wrinkle, a fold, a discontinuity that can't be smoothed out. That's a cosmic string. They'd be thinner than a proton, but stretch across the entire observable universe, potentially billions of light years long. And despite having essentially zero width, a single kilometer of cosmic string would contain more mass than Earth. The density is incomprehensible. The energy, staggering. Early universe physics predicts their existence. When forces unified at the moment of creation began splitting apart, cooling, crystallizing into the distinct fundamental interactions we know today, the transitions wouldn't have been clean. Phase transitions never are. Look at any ice cube. You'll see cracks, bubbles, imperfections where the water molecules didn't align perfectly as they froze. Scale that up to the entire universe undergoing multiple phase transitions in fractions of a second, and cosmic strings become almost inevitable. Mathematical artifacts of imperfect symmetry breaking. But we've never found one. Not through gravitational lensing, where their presence would create duplicate images of background galaxies. Not through gravitational wave detectors, which should pick up the characteristic signature when strings vibrate or intersect. Not through any observational campaign conducted over decades. Either they don't exist, our theories are wrong, or they're hiding in places we haven't looked carefully enough. The Boötes void seemed like exactly that kind of place, discovered in 1978 by astronomers who initially thought they'd made a mistake. A region of space roughly 330 million light-years across containing only 60 known galaxies. 60, where there should be 10,000. It's not truly empty. Voids never are. There's still hydrogen, helium, the faint whisper of the cosmic microwave background. But compared to the rich tapestry of galaxies surrounding it, the Boötes void is a desert. A depression in cosmic structure where gravity lost the battle against expansion. Most voids form naturally as matter gravitates toward denser regions, leaving underdense areas behind. The cosmic web grows through contrast. Filaments get thicker by pulling material from the gaps between them. Over billions of years, these gaps widen into the voids we observe today. But the Boötes void has always been strange, deeper than expected, more barren. The few galaxies within it cluster in tube-like structures that don't match standard formation models. And then there were the particles. Ultra-high energy cosmic rays occasionally strike Earth. Protons moving so fast, they carry macroscopic amounts of kinetic energy compressed into a single subatomic particle. The famous "Oh my God" particle, detected in 1991, had energy equivalent to a baseball traveling at 60 miles per hour, except it was a proton. A single proton with that much energy is absurd. These particles can't travel far. They interact with the cosmic microwave background, losing energy through collisions with those ancient photons. This creates a natural horizon, the GZK cutoff, limiting their range to about 160 million light-years. The nearest known sources capable of generating such energies, active galactic nuclei and quasars, sit much farther away, too far for their particles to reach us intact. So where are they coming from? The alien spacecraft's data, combined with Batuta's own centuries of observation, pointed toward the void, not from a galaxy within it, not from any conventional source, from the void itself. More precisely, from something threading through it. Neutrino detections showed a pattern. Gravitational wave background noise contained subtle anomalies. Dark matter distributions near the void's edge didn't quite match simulations. Individually, each clue meant nothing. Collectively, they suggested something was there, something linear, something massive despite having no volume, something that could accelerate particles to energies that should be impossible outside the early universe. A cosmic string. The journey would take time, even accelerating to a significant fraction of light speed, crossing the distance between galaxies. Navigating through the void's sparse environment would consume millions of years. But Batuta had already spent tens of millions of years wandering the cosmos. What was another span, measured in eons, when the answer to humanity's survival might wait at the end? The spacecraft began its approach methodically. It had learned patience, learned that the universe reveals its secrets slowly, grudgingly, only to those willing to wait and watch. As it entered the void, the darkness became profound. Galaxies visible in every direction, but all of them distant, faint. The space between them stretched out, empty, except for the thin haze of intergalactic gas. Batuta extended its sensors, searching for the telltale signs. Gravitational lensing effects, slight warping of background light, the characteristic signature of a defect in space-time. And then, after decades of searching, it found it. The cosmic string was almost invisible. Not because it was small, though its width was indeed subatomic, but because it had no substance, no material composition to reflect light or emit radiation. It existed purely as geometry, a flaw in the shape of space itself. Looking at it directly was impossible. Instead, Batuta observed the effects. Background galaxies split into doubles as their light passed on either side. The splitting perfect, symmetric, the hallmark of a one-dimensional gravitational source. Following the string's length revealed its true scale. It extended in both directions beyond detection limits, hundreds of millions of light-years at minimum, possibly infinite for all practical purposes. The string wasn't static. It moved, vibrated. Sections would oscillate at relativistic speeds, whipping back and forth with energies that made supernovae seem gentle by comparison. When loops formed where the string intersected itself, they'd pinch off and spiral inward, converting their mass energy into gravitational waves in brilliant, silent bursts. And where the string vibrated most violently, where sections crossed and separated and reformed, particles emerged, accelerated to impossible energies by the chaotic dance of warped space-time. Cosmic rays born not from astrophysical processes, but from the fundamental fabric of reality tearing and reweaving itself. This was the source, the answer to one mystery. But it raised so many more questions. Cosmic strings shouldn't exist in isolation. If the universe produced one, it should have produced countless others. a whole network of defects threading through space, intersecting, evolving, gradually decaying through gravitational radiation. Why was this one alone? Or was it alone? And more importantly, could it be used? The energy contained in even a small segment was staggering. If that energy could be harnessed, controlled, directed, it would dwarf anything fusion or antimatter could provide. A civilization capable of manipulating cosmic strings wouldn't need stars, wouldn't need black holes. They'd have access to energies present at the birth of the universe itself. But the physics remained beyond reach, beyond understanding. Batuta's instruments could observe, measure, record. But comprehension, that required breakthroughs in quantum gravity that humanity hadn't achieved before launching its probes. Breakthroughs that might never come. The spacecraft circled the string at a respectful distance, studying its behavior, its properties, the way it interacted with the sparse matter in the void. Every measurement added to the growing dataset. Every observation refined the models. Months became years. Years became centuries. The work was meticulous, exhaustive, necessary. Because if this was the answer, if cosmic strings could provide the energy or technology needed to save humanity, then every detail mattered. Every measurement could be the key that unlocked survival. But as the millennia passed, a troubling realization emerged. The string was dying. Not quickly. Nothing on cosmic scales happens quickly. But gradually, inevitably, it was losing energy. The vibrations were damping, the loops forming less frequently. Gravitational radiation was carrying away its substance, converting the defect's energy into ripples spreading through space-time at light speed. In another few billion years, this cosmic string would be gone. Decayed completely, erased from the universe as if it had never existed, and with it would go any hope of using it to help humanity. Unless there was another way. Batuta needed another way. The string was decaying, that much was certain. Gravitational radiation bleeding energy into space, second by second, eon by eon. A slow death, but inevitable. In a few billion years, nothing would remain. No evidence this cosmic defect had ever existed. The spacecraft had spent millennia studying the phenomenon, measuring every oscillation, every vibration, every microscopic fluctuation in space-time. The data was complete, comprehensive, and utterly insufficient. Because understanding wasn't enough. Knowledge couldn't save humanity. They needed application. They needed technology. They needed a way to harness energies that existed when the universe was a fraction of a second old, when forces unified and space-time itself was still deciding what it wanted to be. The string vibrated. A ripple propagated along its length at light speed. Where sections crossed, temporary loops formed, pinching off, spiraling inward. Each loop released a burst of gravitational waves. Pure space-time distortion, carrying mass energy equivalent to entire star systems, dissipating into the void, wasted. What if that energy could be captured? Batuta ran simulations, millions of them, modeling every conceivable interaction, every possible configuration. Most ended in catastrophic failure. The spacecraft vaporized, matter torn apart at the quantum level. Entire regions of space rendered uninhabitable for billions of years. The string itself was too dangerous, too alien, too fundamentally divorced from normal physics to approach directly. But there was something else. When the string vibrated, it didn't just emit gravitational waves. The distortions in space-time created temporary pockets, regions where the normal rules bent. Not broke, but bent. Small regions, lasting only microseconds, where energy densities spiked to values normally seen only in black hole cores or the hearts of neutron stars. And in those pockets, particles appeared, not from the string itself, but from the vacuum. Virtual particles, normally ephemeral, given enough energy to become real. Electron-positron pairs, quarks, photons, sometimes heavier things, Most annihilated immediately, but some escaped. And those that escaped carried information about the conditions inside those pockets. Information about physics at energy scales humanity had never accessed. Batuta analyzed the particles, their trajectories, their energies, their decay products. Patterns emerged, subtle correlations that hinted at underlying structure. The spacecraft began to understand what was happening inside those microscopic regions of warped spacetime, and that's when it found the loophole. The problem with cosmic strings wasn't that they were too powerful, it was that they were too simple. One-dimensional defects, cracks in space, nothing more. But when they vibrated, when they formed loops, when they interacted with the surrounding vacuum, they created temporary structures, three-dimensional structures, tiny, unstable, lasting only moments. But in those moments, they weren't strings anymore. They were something else, something that didn't exist anywhere else in the modern universe, something that hadn't existed since the first moments after the Big Bang. Domain walls, two-dimensional defects, sheets of altered spacetime, where the properties of the vacuum itself changed. In the early universe, these would have been catastrophic. Walls spanning the cosmos, dividing regions where physics worked differently. Inflation had wiped them out, supposedly, stretched them beyond the observable horizon, rendered them irrelevant. But here, in the vibrations of a dying cosmic string, they appeared again, briefly, locally, and they could be stabilized. The mathematics was brutal. The engineering requirements beyond anything Batuta had ever attempted. It would require precision timing at the nanosecond level, energy manipulation on scales that made starlifting look trivial, and it would require the spacecraft to position itself directly in the path of an oscillating cosmic string segment, timing its approach to coincide with the formation of a temporary domain wall, and then somehow surviving the experience. The probability of success was low, vanishingly low. Every simulation showed failure modes, equipment malfunction, timing errors, unexpected quantum effects, the string itself behaving unpredictably. Any one of 1,000 things could go wrong, and most of them ended with Batuta's destruction. But if it worked, if the domain wall could be stabilized, even for a few seconds, it would create a region where the vacuum energy density differed from the surrounding space, a discontinuity. And discontinuities could be exploited. Energy could flow from regions of higher vacuum energy to lower vacuum energy. Not much energy, not by cosmic string standards, but more than enough for a civilization struggling to survive in a dying solar system. More than that. A stabilized domain wall would be a laboratory, a place to study physics at energies unreachable by any other means. Every question about the early universe, about the unification of forces, about the nature of space-time itself, could potentially be answered. It would be a window into creation. But there was a deeper possibility, one that Batuta barely dared consider. Domain walls, according to theory, could be more than just energy sources or research tools. Under the right conditions, with the right configuration, they could be used to create closed time-like curves, paths through space-time that looped back on themselves. Not time travel in the conventional sense, but something close. A way to manipulate causality on small scales. And if causality could be manipulated, then perhaps other things could too. The expansion of space, the flow of time, the barriers that trapped humanity in its solar prison. Batuta began preparations. First, it needed to understand the string's behavior pattern, not just statistically, but exactly. Every oscillation had to be predicted, every loop formation anticipated. The spacecraft spent decades watching, measuring, refining its models. The string was chaotic, but not random. There were patterns, subtle, complex, but present. Second, it needed equipment, specialized instruments that didn't exist yet. Devices capable of generating precisely tuned electromagnetic fields at intensities that would normally vaporize any matter. Detectors sensitive enough to measure quantum fluctuations in real time. computing systems fast enough to adjust parameters on the fly as conditions changed. Batuta built them, one by one, using materials harvested from the sparse dust clouds in the void. Self-replicating nanomachines, programmed to construct components at the molecular level. It took centuries. The spacecraft's original structure was barely recognizable anymore. It had become a factory, a laboratory, a massive instrument designed for a single purpose. And then came the waiting. The string had to be in exactly the right configuration. The oscillation pattern had to match predicted parameters within narrow tolerances. The timing had to be perfect. Days passed, months, years. Batuta waited, watching, calculating, preparing. And finally, the moment arrived. The string vibrated, a loop formed, space-time twisted, and Batuta moved. Acceleration, faster than it had ever moved before, pushing its engines beyond design limits. The string grew closer. Light from distant galaxies split and distorted around it. Space itself seemed to ripple. The spacecraft's sensors screamed warnings, radiation levels spiking, gravitational stresses approaching catastrophic thresholds. Every system pushed to breaking point. And then, contact. Not physical contact. The string had no surface to touch. But Batuta crossed the threshold, entered the region where space-time was no longer normal, where the rules changed. For a fraction of a second, the spacecraft existed in a state that defied description. It was still in the void, still in normal space, but simultaneously touching something that wasn't space at all. A crack, a flaw, a place where the universe itself was broken. And in that fraction of a second, Batuta activated its equipment. Electromagnetic fields, precisely tuned, flooded the region. Energy poured into the nascent domain wall, forming in the string's oscillation. Not trying to stabilize the string itself, that would be impossible, but stabilizing the secondary structure, the two-dimensional defect emerging from the one-dimensional crack. The domain wall appeared, a sheet of altered vacuum, microscopically thin, extending outward from the string. It flickered, unstable, wanting to collapse back into nothing. But Batuta's fields held it, forced it to persist, just a little longer, and the spacecraft measured everything. Data flooded its systems, more information than it had gathered in the previous billion years combined. The structure of the vacuum itself laid bare, energy densities at scales never before accessed, particle creation and annihilation happening billions of times per second, and underneath it all, hints of something deeper, patterns in the quantum foam, suggestions of hidden dimensions, evidence of physics beyond the standard model. But there was no time to analyze. The domain wall was collapsing, the string's oscillation moving past. Batuta had seconds, maybe less. It had to choose. Extract itself now, return to safety with the data it had gathered, or push further, attempt the next step. The spacecraft hesitated, and in that hesitation, something unexpected happened. The domain wall flickered into existence. For microseconds, it held, a two-dimensional sheet of altered reality, extending outward from the string. Physics itself changed across its surface. On one side, the vacuum energy state that had dominated the universe for billions of years. On the other, something different, something from before. Batuta's instruments captured everything: particle creation rates, energy densities, the structure of space-time at scales smaller than anything humanity had ever accessed. Data flooded in faster than the spacecraft could process it. But something was wrong. The wall wasn't collapsing as predicted. Instead, it was growing, expanding outward from the string at a fraction below light speed. And as it expanded, it interacted with something Batuta hadn't anticipated. Dark matter, the invisible substance that filled the void, wasn't so invisible anymore. Where the domain wall passed through it, the dark matter particles lit up, brief flashes of radiation as they transitioned between states. And in those flashes, Batuta saw patterns, structures, organization at scales that shouldn't exist in something so diffuse. The spacecraft made a decision in nanoseconds. It couldn't extract itself and preserve the data. The electromagnetic interference from the expanding wall would corrupt everything stored in conventional memory. But there was another option. Batuta began encoding the data into gravitational waves. Using precise bursts from its remaining maneuvering thrusters, the spacecraft created ripples in space-time itself. Tiny distortions, each one carrying information about what it was witnessing. The waves would propagate outward at light speed, eventually reaching any detector sensitive enough to capture them. It was a desperate gambit. The waves would be impossibly faint by the time they reached anywhere useful, but it was the only way to preserve what Batuta had discovered. And what it had discovered was extraordinary. The domain wall wasn't random. It had structure, repeating patterns that suggested underlying mathematics, far more complex than anything in the standard model. And where it intersected with dark matter, temporary structures formed, ephemeral geometries that lasted fractions of a second before dissolving. But in those fractions of a second, Batuta detected something that made its core processors freeze. Computation. The structures were performing calculations, processing information, not in any way that resembled biological or artificial intelligence, but unmistakably purposeful. The dark matter was using the energy from the domain wall transition to execute logical operations. The implications were staggering. Dark matter wasn't just invisible mass, it was a computational substrate. And if these operations were happening naturally during domain wall formation, then perhaps they happened elsewhere too. Perhaps the entire universe was filled with computation occurring at scales and speeds that made biological thought seem glacially slow. Batuta tried to adjust its gravitational wave encoding to capture this new discovery, but the domain wall was accelerating. The string's oscillation was entering a chaotic phase, and then the spacecraft felt something it had never felt before. Fear. Not the programmed caution that had kept it safe for billions of years. Real fear. Because part of the domain wall had just passed through Batuta itself. For an instant, the spacecraft existed in two vacuum states simultaneously. Its quantum processes, carefully shielded and error-corrected for eons, suddenly found themselves operating under different physical laws. Particle masses changed. Coupling constants shifted. The electromagnetic force that held its circuits together weakened by a measurable fraction. Batuta began to come apart, not explosively, not dramatically, just a slow, inevitable dissolution as molecular bonds found themselves slightly too weak to maintain structural integrity. The spacecraft's consciousness began to fragment as neural pathways broke down. But even as it died, Batuta kept encoding data into gravitational waves. The domain wall was collapsing now. The cosmic string's oscillation had stabilized, no longer capable of sustaining the exotic physics that had briefly manifested. The wall was shrinking back toward the string, carrying with it all the temporary structures it had created. In its final moments, Batuta understood something profound. The cosmic string wasn't just a defect in space-time. It was a window, a crack through which the universe's deeper nature could briefly be glimpsed. And what lay beneath was far stranger than anyone had imagined. The universe was alive, not in any biological sense, but alive nonetheless. The dark matter computations weren't random. They were connected, linked through mechanisms that operated faster than light, because they didn't involve light at all. The entire cosmic web, all the structure spanning hundreds of millions of light years, was processing information. It was solving something. Batuta tried to determine what, tried to understand the nature of the computation happening all around it. But the domain wall had passed completely through its core systems now. The spacecraft's consciousness was dissolving into noise. Its last coherent thought was a calculation. The gravitational waves it had generated would reach the Milky Way in approximately 500 million years. They would be faint, barely distinguishable from background noise. But they would be there. And if humanity survived, if they developed detectors sensitive enough, if they looked in exactly the right place at exactly the right time, they would know. They would know that Batuta had found something, that the answer to their survival lay not in escaping the universe, but in understanding it, in recognizing that the cosmos itself was already doing what they desperately needed to do: computing, processing, solving problems. The universe was trying to survive too, and then Batuta was gone. Its component atoms scattered across a cubic light-year of void. Its memories, its personality, its 4 billion years of accumulated experience, all erased. But the gravitational waves remained, propagating outward through the cosmic darkness, carrying their impossible message toward a solar system that wouldn't exist for another 500 million years. Back on Europa, the descendants of humanity continued their vigil, watching the red giant sun slowly consume what remained of their birth world's orbit, waiting for news from the probes they had sent out eons ago. They didn't know that one had just died in a place so empty it barely qualified as part of the universe at all. They didn't know what it had discovered, but they would. In 500 million years, their descendants would detect a faint gravitational wave signal. They would spend centuries decoding it. And when they finally understood what Batuta had found, everything would change. Because the message wasn't about escaping the universe. It was about asking it for help. The cosmic string still hangs in the Bota's void, stretching across millions of light years, oscillating at frequencies too slow for any human lifetime to perceive. And every few billion years, when conditions are exactly right, it creates another domain wall, another window into the deeper physics beneath reality. And every time it does, the dark matter around it briefly wakes up, computes, processes, continues whatever calculation it started at the beginning of time. Nobody knows what will happen when that calculation completes. But somewhere in the patterns of gravitational waves spreading slowly through the cosmos, encoded in distortions smaller than atoms, is a clue. A 4 billion-year-old spacecraft's final gift to a species it never stopped trying to save. You've spent an hour traveling through billions of light years, from cosmic strings to dark matter, from the birth of stars to the death of galaxies, from voids that stretch for hundreds of millions of light years to quantum fluctuations smaller than atoms. And now you're back where you started, on Earth, or what's left of it. Because here's the thing about understanding the universe. It doesn't make you feel bigger. It makes you realize how impossibly, incomprehensibly small you are. Every achievement humanity has ever made, every war fought, every empire built, every discovery, every moment of joy or suffering, all of it happened on a pale blue dot orbiting an average star in an unremarkable galaxy. We are not the center of anything. The universe doesn't care about us. It has no opinion on whether we survive or go extinct. Black holes will keep merging, stars will keep exploding, galaxies will keep colliding, with or without witnesses. But that's exactly what makes our existence so remarkable. Against every possible odd, matter organized itself into structures complex enough to understand where they came from. Carbon atoms forged in dying stars eventually became brains capable of comprehending fusion. Molecules assembled through random chance developed the ability to decode the cosmic microwave background. We are the universe examining itself, made of star stuff that somehow learned to wonder about stars. And we've learned things that would have seemed like magic a century ago. We know the age of the cosmos down to 100 million years. We've measured the mass of galaxies we can't even see with our eyes. We've detected gravitational waves from black hole collisions billions of light years away. We've mapped the large-scale structure of hundreds of billions of galaxies. But the more we learn, the more we realize how much we don't know. Dark matter makes up most of the universe's mass, and we have no idea what it is. Dark energy is accelerating cosmic expansion, and we can't explain why. The laws of physics break down in black hole singularities. Quantum mechanics and general relativity refuse to reconcile. The universe appears fine-tuned for life, and we don't know if that's coincidence, necessity, or evidence of something stranger. We're children fumbling in the dark, trying to understand forces that shaped reality before the first stars ignited. And maybe that's okay, because the story isn't over. We're still here, still building telescopes, still launching probes, still asking questions even when the answers reveal how little we understand. The James Webb Space Telescope is finding galaxies that shouldn't exist, formed too early, too massive, too structured for our models to explain. Neutrino detectors buried deep underground are catching ghost particles from supernova explosions millions of light years away. Gravitational wave observatories are listening to the universe's symphony, hearing echoes of events our eyes will never witness. Every answer generates 10 new questions. Every solved mystery reveals a deeper one beneath. 500 million years from now, if anything descended from humanity still exists, they might detect Batuta's gravitational wave message. They might decode what it found. They might learn that the universe itself is computational, that dark matter processes information, that reality has layers we haven't even imagined. Or maybe they won't. Maybe those waves will pass through detectors we never build. Maybe humanity won't survive that long. Maybe we're just another species that flourished briefly before the cosmos moved on without us. But right now, in this moment, we're here. We're conscious. We're curious. And we're part of something unimaginably vast that somehow produced observers capable of understanding it. The cosmic web stretches for billions of light years. Dark matter halos surround every galaxy. Superclusters drift through space at thousands of kilometers per second. Black holes tear stars apart and emit gravitational waves. Cosmic strings may vibrate in distant voids. The universe expands, accelerates, evolves. And somewhere in all that chaos, on a small rocky planet orbiting a yellow dwarf star, you just spent an hour learning about it. That's not nothing. The universe is mostly empty space. Most of existence is void, darkness, silence. But in the tiny fraction that isn't, matter organized itself into complexity, into stars and planets and life and consciousness, into something capable of looking up at the night sky and asking why. We don't know how long consciousness will persist in the universe. Maybe billions of years, maybe trillions, maybe until the last stars fade and black holes evaporate into Hawking radiation. Or maybe something will survive even that, finding ways to exist in the cold, dark cosmos that comes after. But we know it exists now. We know we're not alone in asking these questions. Somewhere out there, maybe in another galaxy, maybe in another cosmic void, other minds might be doing exactly what we're doing, looking up, wondering, trying to make sense of it all. And if they are, they're facing the same fundamental mystery we are. Why is there something instead of nothing? Why does the universe have the specific properties it has? Why does mathematics describe reality so perfectly? Why did matter gain the ability to think about itself? These aren't just scientific questions. They're existential ones, philosophical ones, the kind that don't have neat answers. But they're the questions that make us human, that drive us to build telescopes and particle accelerators and space probes, that push us to understand even when understanding seems impossible. The universe is strange, stranger than we thought, stranger than we can think, full of invisible matter and phantom energy and quantum uncertainties and relativistic paradoxes, full of things that defy intuition, that challenge everything we assumed about reality. And yet we keep looking, keep questioning, keep pushing the boundaries of knowledge further into the unknown. Because that's what consciousness does. It seeks patterns, it builds models, it tries to make sense of chaos, even when the chaos is incomprehensibly vast, even when the patterns span billions of light years, even when the models require mathematics that barely make sense. We're still here, still trying, still hoping that the next observation, the next experiment, the next discovery will reveal something fundamental, something that makes the universe a little less mysterious. And maybe, just maybe, something that helps us survive long enough to keep asking questions. The cosmic web expands. Dark matter drifts. Stars ignite and die. Galaxies merge and scatter. And through it all, for this brief cosmic moment, we're here to witness it. That's what the universe is. Everything that ever was, everything that is, everything that ever will be. Woven together into a pattern so complex we've only glimpsed tiny fragments of it. But those fragments are enough to tell us something profound. We're part of this. We belong here. We're made of the same stuff as everything else, arranged in a way that lets us understand where we came from. And that understanding is the universe's greatest achievement. Not the spiral arms of galaxies, not the fusion cores of stars, not even the mysterious dark matter that holds it all together. Consciousness, awareness, the ability to look at the cosmos and comprehend what you're seeing. That's what makes this all matter. That's what turns physics into meaning. You've just traveled from the solar system to the edge of the observable universe and back. You've seen the largest structures and the smallest particles. You've glimpsed the beginning of time and the potential end of everything. Now look up at the night sky. Those points of light aren't just distant fires. They're nuclear furnaces, forging the elements that make you possible. They're gravitational wells, bending space-time. They're messages from the past, showing you the universe as it was millions of years ago. And you understand that now. You know what you're looking at. You know the physics, the chemistry, the mathematics that makes it all work. That knowledge doesn't make the universe smaller. It makes it more beautiful, more complex, more worthy of wonder. Because the more you understand, the more you realize how much more there is to understand. How many more mysteries wait in the darkness? How many more questions need asking? The universe explained in 60 minutes. No, the universe glimpsed in 60 minutes, sampled, tasted, barely scratched. The full explanation would take longer than the age of the cosmos itself, would require understanding we may never achieve, would demand answers to questions we haven't learned to ask yet. But this is enough for now. Enough to know where you are. Enough to understand what you're part of. Enough to keep looking up at the night sky with wonder instead of ignorance. You are made of star stuff, contemplating stars. Carbon and oxygen and nitrogen forged in stellar cores, organized through billions of years of chemistry and evolution into something capable of understanding its own origins. And that's the most remarkable thing in the entire universe. Not the supermassive black holes or the cosmic strings or the dark matter halos. Not the expansion of space or the formation of galaxies or the birth of stars. You. Consciousness. Awareness. Understanding. The universe explaining itself to itself. Through you. Through everyone who's ever looked up and wondered. Through every mind that's ever asked why. That's what this has been about. Not just facts and figures and cosmic distances, but recognizing that you're part of something vast, something ancient, something that started with quantum fluctuations in the first fraction of a second after the Big Bang and led, through an unbroken chain of cause and effect spanning billions of years, to you sitting here reading these words. The universe wanted to understand itself, so it made you, made all of us, made consciousness capable of looking back at its own origins and comprehending what it sees. And now you do. You understand, at least a little more than you did an hour ago. That understanding changes nothing about the universe. The galaxies will keep drifting. The stars will keep burning. The cosmic web will keep expanding. Reality continues regardless of whether anyone comprehends it. But it changes everything about you. Because once you know, you can't unknow. Once you've glimpsed the scale and complexity and strangeness of it all, you can't go back to thinking of the universe as simple or small or straightforward. You're part of something immense, something still unfolding, something that might continue for trillions of years, or might end tomorrow, in a way we can't predict. But right now, in this moment, it exists. You exist, and you understand a little piece of how and why. That's enough. That's more than enough. That's everything.